Okay, our next topic is final value theorem in Laplace transform. If the Laplace transform of x of t is denoted by x of s, then according to the final value of theorem, limit t tends to infinity x of t should be equal to limit s tends to 0 s into x of s. Now let us prove this statement. In order to prove this final value theorem, we need to know the time differentiation property of Laplace transform that we have discussed under topic initial value theorem. Just to go through that video also, okay, right? Anyway, I'm going to explain the time differentiation property once again here also, okay? According to the time differentiation property, the Laplace transform of the first derivative of the signal x of t, that is Laplace transform of d by dt of x of t, that should be equal to s into x of s minus small letter x of 0. This is the statement for time differentiation property. So okay, let us mark this equation number 1, and we know that the Laplace transform of x of t, that is equal to del 0 to infinity x of t e raised to minus ft dt. That is the basic equation for Laplace transform. Okay, so therefore we can write the Laplace transform of this one, d by dt of x of t, can be rewritten as, here we have x of t, in the RHS side of this equation also we have x of t. Laplace transform of x of t is equal to x of t e raised to minus ft dt. Therefore, Laplace transform of this one should be just replace here x of t with d by dt of x of t. Okay, this one. Here we replace it. Then followed by e raised to minus ft dt. Okay, let us mark this equation as equation number 2. And if we compare equation 1 and 2, the LHS of both equations are same. So let us say that the RHS should be same. So, okay, right. The LHS of both equations are right, therefore RHS should be same. What about the RHS of equation number 1? That is equal to this one, and RHS of equation number 2, that is integral 0 to infinity d by dt of x of t e raised to minus ft dt. Okay, that is the RHS of equation number 2. That is equal to the RHS of equation number 1, that is s into x of s minus x of 0. Take the limit f tends to 0 on both sides in this equation, then we are getting limit f tends to 0 LHS. Then we will be getting like this, limit f tends to 0 LHS, the entire LHS is written here, that is equal to, if we take the limit f tends to 0 on right hand side of this equation, we are getting the equation like this. Okay, now if the value of s in the LHS equal to 0, what will happen? If s is equal to 0, here we have a single term containing yes e raised to minus s. If you substitute s equal to 0 in here, then we are getting e raised to 0. Okay, right? So let us write that also. Integral d by dt of x of t e raised to, putting s equal to 0. So e raised to 0 dt. And let us expand the bracket in the RHS also. S equal to 0 s x of s. Then here we do not have any term containing s, so limit f tends to 0 is not applicable here. Okay, so let us write it as x of 0 itself. Could you get that concept? Here we do not have any term containing s, therefore limit doesn't affect this x of 0. Okay, so simply we return as x of 0 itself. Okay, right? Everybody knows integration and differentiation are opposite to each other. That means suppose we have a variable x, and here I'm taking the derivative of x with respect to t. Okay, that is written here. Then I'm getting d by dt of x. Okay, d by dt of this function x. If I integrate this function that is written here, integral of this one, of course, that with respect to dt itself. Okay, the result should be x itself, because integration and differentiation are opposite to each other. If we integrate the derivative, we can reproduce the original variable itself. That is explained here. Okay. If we apply this concept in the left hand side of this equation, what will be the result of this left hand side? Here it is equivalent to the second line, right? This one. Okay. Integral of a derivative with respect to dt itself. Here dt, here we have integral with respect to dt itself. Okay. This equation is equivalent to the second one. Then here I have marked it. What is written over d by dt of that function? Here d by dt of x. What about this one? D by dt of x of t. Okay. Then the result should be, of course, x of t itself. Here we have only single x itself. X is independent. That's why now x of t term here. Then the result is x of t. If we compare these two equations, we can say that LHS of this one is equal to x of t. Okay, RHS is the same itself. Okay, x of s minus x of 0. And here we have a limit to be applied. Now let us apply the limit in the left hand side. If I am putting infinity for t, I'm getting x of infinity. I'm applying the upper limit minus lower limit x of 0. Okay, right. That is equal to limit f tends to 0 as x of s minus x of 0. Here we have x of minus x of 0 minus x of 0. Then both can be cancelled each other. Okay. Then the remaining thing is x of 0 is equal to limit f tends to 0 as x of s. What is x of infinity? How can we express x of infinity in some another manner? Let us write here the value of t is equal to infinity. So I'm writing limit t tends to infinity x of t. Okay, right? That is equal to x of t itself. That is equal to this one. S tends to infinity as x of s. Okay, that is the required result to be proved. Hence, we proved the result. Okay, thank you.